Hey, let's take a look at this workbook page about Newton's third law and internal forces. There is a shortcut that you can do whenever you have a system of objects. Usually a system of objects is when you have objects that are attached together, like by a string or a rope or pushing each other in some form or fashion where pretty much everything moves with the same acceleration because they are connected somehow. We always start our force problems with a free body diagram, so we will start with the caboose. It's got the gravitational force. Actually, all of them have gravitational force. Right? Since we do have a grid background, we are looking for correct sizes of the forces relative to each other. So since one is 3, one is 2, one is 1, right, I've made those forces proportional, and I have named them different things because they are technically 3 different gravitational forces on our 3 different objects. This train car, or this set of train cars, is not accelerating through the ground, nor is it being ejected into the air. We know that the forces in the vertical direction should be balanced. So I'm just going to draw 3 upwards balancing forces, name them Fn, 3, 2, 1. Okay? And now we can actually get to the interesting part, which is the horizontal forces that are acting on each of these carts. So on our caboose, they've called it F3, but I would like to be more formal here. I would like to call this force of train car number 2 on train car number 3, right? So if we go in order from there's the engine car, then there's train car 1, then there's train car 2, then there's train car 3, right? So 3 is getting pulled forward by train cart number 2, right? Remember that forces are always between pairs of objects, and you need to be able to identify the type of force and the 2 objects that are interacting. So cart number 2 pulls the caboose cart number 3 to the right. Cool. We also know that Newton's third law is a thing, right? For every action, there's an equal and opposite reaction. What does that mean? Well, it means that if force 2 on 3 exists, then force 3 on 2 also needs to exist. So these 2 forces here in red, right, are a Newton's third law pair. Notice they are equal in size, opposite in direction, and they act on different objects, right? Normal force and gravity are not third law pairs. Those are actually Newton's first law, balanced forces examples. It's an entirely different mechanism. Okay, so Newton's third law there in red. Okay, after we do our free body diagram, so we're finished with the free body diagram for number 3, right? Once we have our free body diagram complete, we can then write our net force equation. You slap down Newton's second law, sigma F is equal to ma, right? You then expand sigma F based on how many forces you have acting in your particular direction. In this case, well, you just have that one red force, right, that is acting on mass number 3, right, our caboose cart. Right, so you got to be specific, right? It's not just any mass. It's specifically, I'm looking at the free body diagram for cart number 3. I'm going to use the mass for cart number 3. As I plug that in, we get that F2 on 3 must be equal to 6,000. Okay, done with that. On to the 2,000 kilogram cart, right? We know that this whole entire train is accelerating to the right at 2 meters per second squared. That means there should be a rightward force, right, on that 2,000 kilogram cart. Right? You look at the picture, you're like, oh yeah, right? This middle cart is getting pulled by the cart that's on its right, right? It's getting pulled by the 1,000 kilogram car, right? So not only is there a rightward force, right, on this cart, but because it is accelerating to the right, I know that this rightward force needs to be bigger than this leftward force, right? So something that looks like this, and I'm going to call it by its full name, right? They want you to call it F2, but I think it's more illuminating to call it F1 on 2, right? Because it's the first cart pulling on the second cart, right? And that's it for this free body diagram, right? After we do our free body diagram, our next step, slap down Newton's second law. Oh, wait, sorry. I forgot, the Newton's third law pair, right, while we're thinking about it, right, on the 1,000 kilogram cart, and then, okay, Newton's second law. Okay, when all that math is said and done, we get that the force of 1 on 2, the force otherwise known as F2, right, is 10,000 newtons. And that's how we do that. So for the third cart, which I guess is actually the first cart with the way that I've named them, we have that third law pair, right? Force of 1 on 2 and force of 2 on 1. That mirrored naming is like the dead giveaway, right? These two forces must be equal and opposite and act on different objects. We know that this first cart is accelerating to the right, so the net force is supposed to be the right. That means that the force that this engine car exerts must be bigger than F2 on 1. Right, so this is from that locomotive engine there in front. Kind of plugging in some of my numbers from last time, from the previous parts, right? I come up with the force of the engine car, what they want to call F1, is equal to 12,000 newtons. Right, so with a little bit of cleverness there, right, with your Newton's third law pairs, you essentially can substitute numbers from one part into the other part. If you wanted to be really formal with this, you could set this up as like, an algebra system of equations where you have three unknowns, right, F1, F2, and F3, right? And so if you have three unknowns, you need to have three equations, three net force equations in order to solve for them, right, using whatever algebra techniques you learned from your math teacher. Okay, there is a shortcut. And I think it's really important for us to understand like what a system is, because the AP Physics 1 exam talks about systems of objects all the time. So we want to consider, okay, that's fine. I want to consider the system consisting of the 2,000 and the 3,000 kilogram carts. So up there in the top, I've boxed it in pink, right? And looking at that, you can see that the red forces, right, are entirely encompassed within this system, right? This pair of forces are called internal forces. So your Newton's third law pairs, if you define your system in such a way, right, that your Newton's third law pairs are internal, then your problem might become much simpler, right? So looking at my free body diagram, right, technically your normal force and your gravitational forces, those are external to the 2,000, 3,000 cart system, right? Because those two forces are coming from objects that are outside of the system, okay? The force of gravity is from the earth pulling on each of the carts, right? The normal force is from the ground supporting each of the carts, right? The red forces there on the inside, it's 2,000 pulling on 3,000 and 3,000 pulling on 2,000, which are defined to be part of the system. So the neat part about this is they cancel out. And the only net external force, I should say, we have acting on our system is that little one in green, right? The force known as F2, right? If we wanted to call that force by its full name, it's going to be force of 1 on 2, right? Because it's the 1,000 cart pulling on the 2,000 cart, but the 2,000 cart is technically part of the system, so yeah, it's external to the system. I usually tweak my Newton's second law equation a little bit. It says I'm going to do something slightly fancy. Right? I usually do a subscript ext for external on my net force, and then to remind myself, like, well, what object am I looking at? Well, I'm not looking at an object. I'm looking at a system of objects. And so I would want to consider the system's total mass, right, when setting up my Newton's second law equation. So then when I do that, right, I crunch my numbers and I get 10,000 newtons, the same as before. Okay. For this second one, let me box my system now. I'm looking at the 2,000 and 1,000 kilogram cars. All right, so that's there in turquoise. You can see my green forces, right? The 2,000 on the 1,000 and the 1,000 on the 2,000. These are now internal to the system. We don't have to worry about them because they cancel out. Right? However, okay, the forces that would be poking out of this this turquoise box, right? We've got the red one pointing to the left, and we've got the yellow one from the engine car, right, pulling to the right. So I've got F3 on 2 and F engine car. If I had started here, this wouldn't be a particularly solvable equation to start with. You still have 2 unknowns if you just went with this. I don't usually do this. My favorite technique is to lump all of my objects together, right, to treat this as a system as a whole. Usually I do this to find the acceleration of the whole entire system. Usually it's kind of the other way around. You're given one of the forces and you have to determine the acceleration first. But either way, my inclination is to just lump everything together in a giant thing that I call the super block, right? It's just everything in the system accelerates at the same magnitude, right? Not necessarily even the same direction in the case of an Atwoods or a modified Atwoods. But if they're all kind of moving the same, we should be able to figure out the net force on the system in order to find the acceleration. So I got a little sloppy there with my normal force and gravitational force. It's fine, right? This systems technique, I don't think College Board would ever ask you to explicitly do it. It's a shortcut. It's a well understood shortcut. But as far as making you draw a free body diagram for the whole entire system, I think it's kind of unlikely. So this is it. I mean, this is the whole thing, right? We did the net external force is equal to the total system mass multiplied by the acceleration. The total mass of my system, 3,000 plus 2,000 plus 1,000, right? That's 6,000 times 2, which was the stated acceleration of the system. That means the net external force on this mysteriously frictionless train must be 12,000 newtons. And that is the shortcut for solving systems of objects.